Okay, so we are perfect on time, and we can introduce our next speaker. That is Andrés Gomez, administrator at CESGA. And thank you, Andrés, for being here. And I leave you the floor for your presentation.
Okay, good afternoon, and thank you for inviting me to present our activities in quantum computing. I hope that you can see my screen now with the presentation. If you can confirm
Yes,
it.
yes, we can.
Okay. Well, the problem of being one of the last speakers in this session is that almost everything that I want to say has been said before by the other speakers. So maybe you cannot learn nothing now, except maybe a few details or our vision about that. So let me first introduce my organization. CESGA is a supercomputer center that is located in Galicia, in the northwest of Spain, with a public foundation with the board of trustees composed of members of the regional government and members of the National Research Council of Spain. So we are a national facility that is part of a bigger national facility that is the Spanish Supercomputer Network that covers many places in Spain and is led by the National Center that is located in Barcelona. Our mission, and this is important to stress here, is to provide services and make research in the application of high performance computing and communications. But what is important is that we do everything in collaboration with other institutions or entities. Because we are a small foundation, we are only around 40, 50 people, depending on the number of projects that we are running. And we provide services to our users that are mainly universities and research centers around Spain, but also to small companies and big companies that want to make research in high performance computing. And we have to adapt our infrastructure to the needs of our researchers, to the needs of our users that come from a lot of different productive sectors or research area, from bioinformatics to the high energy physics. So the number of needs and the type of requirements that we have is completely different. So we provide completely different resources from high performance computing, cloud environments, big data, or high performance communications. As many other centers in Europe, we have in the future, or in fact currently, three main challenges. One of them is the big data or the industrial data, or what you want, the research data, that we are creating a lot of data that we have to process, and we call high performance data analytics. Of course, the artificial intelligence or machine learning, deep learning area, applying this technology both to create numerical models or to process data. And finally, in the last years, we have the next challenges, the quantum technologies, both quantum computing and quantum communications. In the last 5 years, we started to work in quantum computing. Of course, the first step was understand and learn quantum computing, because we didn't know nothing 5 years ago, and make small internal research projects in order to understand the algorithms, the techniques, the technologies that are behind this new concept of computing. The second one was to leverage a local community. This means to train local researchers, to train local people from universities, from companies, in order to transfer them the things that we learned about quantum computing and about the state of the technology. We deploy, as other centers as we have seen today, several emulators or simulators like Qiskit, Project Q, TensorFlow, Quantum, Kibo, others. everything that can run in our supercomputer. We are lucky because we have a large memory in all the nodes, usually between 128 gigabytes to 4 terabytes of memory. So these servers are really well suited or well fit to fit it to the execution of these simulations. We collaborate with the training students from the university with courses and internships at CESGA. We offer them to be here between 1 month and 2 months working with quantum computing in our supercomputing facilities. And of course, we are pushing companies and public institutions in our region and in Spain to work with these quantum computing technologies. Last year, we started to work in the European project HPCQC. I will talk later about that. And finally, this year, we deploy, as other centers, one QLM of 30 qubits in order to start to have a dedicated platform for quantum computing. Currently, we have between 6 and 7 users from 3 different institutions, plus researchers from CESGA, of course. So we hope that we can create a community around this simulator. But at the beginning of the year, we started to define a strategic plan that we call in Spanish Polo of de Tecnologías Cuánticas, or this means something similar to the Quantum Valley. This means the idea is to have here a set of companies and institutions to work together in quantum technologies that can create a community so our region and in fact Spain can be a European reference in quantum technologies by 2013. This strategic plan has 4 pillars that are important. First of all is the academy, the universities. They have to create the new technicians, the new researchers that understand better than us the quantum technologies and can develop the future in the next 10, 20 years. The second one are the research and technological centers that from our point of view, they have to learn also this technology and create new products, new services based on these technologies. Of course, we cannot create anything if we don't have in board our companies, our local enterprise, the economy that leverage this technology and create products for the future based on the new way for quantum technologies. And finally, the society. We cannot forget them because they are funding us. They will use this kind of services or this kind of products, and they will create a new researchers in the future because they have to transmit to the young people that quantum technologies are really important for the future. The mission of this strategic plan is to achieve a disruptive impulse in the quantum technologies in our region, especially in quantum computing and communications. The first step of this plan has been started at the end of this year. We had the initial seed funding of our regional government coming from European funding. And the idea is to deploy an initial infrastructure composed of one integrated system that join 3 devices or 3 pieces. One is, of course, a quantum computer, a QPU, or at least one QPU. The second one is a classical simulator or emulator of quantum computing. Currently, as I said, we have an Atos QLM of 30 qubits. The idea is to increase this capacity. We don't know if with QLM or another one. And finally, an HPC system exclusive for quantum computing, both for simulation but mainly to work in the new kind of algorithms, hybrid algorithms that we use the QPU and classical algorithms together. We learned today from many presentations that the hybrid computing is really the future. And in this, we believe in that. And I think that is important to take into account that HPC distributed or collocated with QPU is really the future. And finally, we started with deploying a small infrastructure that is a quantum random generator that is there since November this year, and it's only for making experiments about this technology, understand this technology. Other research projects that we are involved and will start next year, one of them is Quantum Spain, that maybe you have some news about that. We are part of the consortium that is proposing this project, and that initially will start next year. The proposal, the aim of this project is to create the first quantum infrastructure around Europe based on the national supercomputer network with at least one computer that developed in Spain to be deployed in Barcelona, but also to create separate infrastructure with people in all the centers with the skills to support our users, our researchers. This is one of the most important things in one supercomputer center. And of course, to make research about algorithms, especially quantum machine learning algorithms, in the universities that will collaborate with us in this project. And we are involved in another second national initiative to develop quantum communications technologies that has three goals. The first one is to research and deploy quantum communication infrastructures. In this case, our idea is to deploy a testbed between Santiago and Vigo, that are two cities in our region that are close. So near enough to deploy a network, an experimental network, 100 kilometers, and to research and of course also leverage quantum algorithms, taking into account also these quantum communication networks for the future. Our participation in NEAX-QC, that is a project that is focused on use cases from industrial users in order to understand better the needs and the capabilities of this new technology in different areas, is around two use cases where we participate with other institutions. In the first one is the quantum natural. Sorry, it's not this one. Should be another one. I'm very sorry. Let me correct because it's not this one. It is this one. Oh, sorry for this mistake. Now it's correct. We are collaborating with the University of Coruña and with one hospital in order to develop quantum rule-based systems that leverage the capacity of quantum computing in order to include in these models the uncertainty of the rules that we have to apply.
Sorry, Andrés. Sorry, but I think that we lost the sharing.
Okay.
The screen sharing.
Now it's working.
No. Okay. Yes. Now, yes. Thank you. Sorry for the interruption.
Sorry, because I did a mistake in the presentation and.
Don't worry. It happens.
And the second one is that we are working in financial applications with one bank that is the HSBC, and again with the University of Coruña, to understand better the quantum algorithm for financial applications. In the first 2 years, we are working in quantum accelerated Monte Carlo for financial applications, and we did an initial state-of-the-art report, and we are now developing the first two set of algorithms that we think that will improve the previous results in the area. But the third activity is one that is related with all the use cases, that is to develop a benchmark suite. a benchmark that using the cases, using the information that we can extract for the cases and from the needs of the cases, the idea is to develop as a benchmark that is a suite, because we don't believe that we can define a single metric in order to analyze and to help the developers of the hardware to fit really the new developments in the needs of the users. This is a typical approach that we have in classical computing, and I think that we should do also in the quantum computer area. So the first idea is to try to understand better the future. It's very difficult, as we can see before, to forecast the evolution of the quantum computer, but clearly we think that in an initial step, the quantum computing will be something similar to an accelerator of the high performance computing. Maybe with one node sharing one or several QPUs. These nodes, a classical node connected with a typical low latency, or maybe a distributed network, as the previous speaker presented. Maybe in the future, because we have this year some initial results, having a quantum network or a quantum internet connecting the GPUs. If we have in mind this broad architecture for the future, and taking into account that our user really, the most important part is to solve the problem, not to develop a quantum algorithm. It's not, they have to solve a problem that they have in chemistry or in physics, in logistics, in one area. Really, the approach is to have a hybrid classical quantum API of a set of based on a set of kernels with a quantum part that is more important than the classical part of in the opposite way, classical more important than quantum, and with several stacks that usually maybe they are mixed, as for example data transmission. So taking into account this architecture is really very important for the future, and is really important for the design of this quantum benchmark suite that we want to develop in next. And let me explain a little bit what's happening with the hybrid classical quantum and why we cannot forget the classical part. Let me explain, for example, one small example that we developed during the COVID lockdown in 2020, thinking about how to calculate eigenvalues of an Hermitian matrix. Our question is, what is the definiteness of the matrix? You know that this is an important problem for many classical algorithms, and that the idea is to know if the eigenvalues of these Hermitian matrix are all positive, all negatives, some positive and some negatives, or maybe one is zero and the rest are positive or negative. In this case, we can define the matrix in 5 categories: positive, positive, semi-definite, negative, and negative, semi-definite, and indefinite. Indefinite, this means that some of the eigenvalues are negative and another one are positive. Solving this problem classically is really very heavy. So one possible solution is to use quantum phase estimation that can be used to calculate the eigenvalues. So you know is that you have an eigenvalue of the matrix M. Then you have the E to the this eigenvalue plus the I is an eigenvalue of the exponential of this matrix with the same eigenvectors. That is important. So if you know the eigenvectors, you can calculate for each one the eigenvalue using the quantum phase estimation. One thing that usually we know or we learn in the quantum algorithms is that if we want to use the quantum phase estimation, we need initially that this phase has to be between 0 and 1. So if we don't know exactly the value of this eigenvalue that can be higher or 1, we can divide this eigenvalue by a value. So we can transform the eigenvalues to the range that we need between 0 and 1. But the problem is what happens if the eigenvalue is 0, is so lower than 0. Well, this is the trick of this algorithm, and I will show later. But the problem is that usually we know the matrix, but we don't know the eigenvalues and the eigenvectors either. So it's very difficult to do that. If we know the eigenvectors, we can solve the problem in parallel, creating a superposition of all the eigenvectors and achieve or return all the eigenvalues at the same time in superposition. But the problem is, as I said, what's happening if the eigenvalues are negative? Well, in fact, you don't need to be this eigenvalue positive. You can make a quantum physics estimation that can work between -0.5 and 0.5 because you have a rotational sieve in the algorithm. So really that we need is the absolute value of these algorithms divided by the constant should be lower than 0.5. But again, which is A in this case. Well, in this case, we can use the classical algorithms. There is a classical theorem that says that you can at least put some limits in the eigenvalues, the low eigenvalue of a matrix and the high eigenvalue of a matrix, only calculating the trace of the square of the matrix. And in this case, if you are lucky, you can classify the matrix as negative, positive, or indefinite, depending of the values of these limits. As I said, for example, if the high limit or the maximum value is lower than 0, in this case, clearly all the eigenvalues are negative. The same happens when we have the limit, the low limit of the minimum value higher than 0. And the third case is that we have the maximum value of the low minor than 0 and higher than 0, the other one. In this case, is clearly indefinite. This needs around n square operations because in fact we have to only calculate the trace of the m square, but we have to calculate only the diagonal elements of this m square. If you are not lucky and you have to use the quantum phase estimation, in this case we can calculate our A, and in the previous algorithms using these values. If we calculate A as using the absolute value of Cmin and Cmass, in this case we are compressing all the eigenvalues to be between 0.5 and 0.5, and we separate. And we don't know exactly the eigenvectors, but we can use several random vectors that will be combinations of the eigenvectors. Because we don't know exactly if we are generating all the eigenvectors, the idea is to generate several random values and calculate only the expectation value of sigma z in the last qubit, in the most significant qubit, that is the sign of the eigenvalues altogether. So we did this second step algorithm, and the problem is that we have to decompose the matrix in a set of Pauli strings because it's the only method that we know. Maybe there are other methods that are better than this, but this is the method that we know. But the problem is that this decomposition needs order 9 to the 3 operations to calculate all the values that we have to introduce in our algorithm. This means that initially it's higher than the number of operations that we have in the classical part of the algorithm, but is initially of the order of the operations that we have in the classical algorithms for calculating this definiteness of the matrix. So the quantum phase algorithm for this algorithm and with the characteristic that we have used have this other number of operations. The problem is that when n is large, mainly the classical part of the algorithm is more expensive than the quantum part of the algorithm. This means that when you analyze a quantum algorithm, you have to take into account both parts, the quantum and the classical part. You cannot say, okay, the quantum algorithm part is faster and the scalability is better than the classical part. You have to take into account what's happened with the classical pre-processing and post-processing that you have to do with the algorithm. Only to say that we did an experiment with 1,500 matrices. Around 60% of them can be classified with the classical part, and around 30% has been classified with the quantum phase estimation algorithm. This is another use of the HPC centers because we had to run more than 3,000 simulations in order to take into account different number of qubits in the auxiliary part of the quantum phase estimation. And this is a very large number of simulation that needs a lot of memory. So HPC can help you, if you are a user, to analyze this kind of algorithm better. Finally, let me introduce the hybrid classical benchmarking that we are developing in HPCQC. We have defined four objectives for this algorithm. One of them is the first one is to help computer architects, programmers, and researchers to design the future quantum computers. The second one is to understand the evolution of the quantum computers. This is the typical objective of benchmarking. Compare the performance of the different platforms and consider other metrics that can be important to understand the quantum computing advantage. For example, if they consume less energy, they can produce better results. They are more scalable, the throughput of the algorithms. Of course, we don't believe that we need or we can achieve a single metrics to define an algorithm. Maybe, for example, this morning we had the IBM proposal for quantum volume and side flops. So we are defining a JSON schema in order to report the information that will include information about the hardware, about the execution, about the stack that has been used for the compilation, and of course, technical details about the QPUs like the placements, the elapsed time, the total elapsed time, the classical elapsed time, the quantum elapsed time, and other metrics specific for the algorithm to understand the performance or the quality of the solution. So to end, because I am 1 minute late, quantum computers in our idea can help HPC to create 4 different quantum advantages. Usually we hear quantum supremacy. That is when we don't know a classical algorithm that can solve a quantum problem that can be solved using quantum capabilities. But we have other quantum advantages. For example, when we can solve problems that really we know how to solve classically, but faster, because our users usually want to solve the problem as fast as possible. The second one is that we can get better solutions that the classical algorithms can provide us. You know, in many optimization algorithms, they are heuristics, and maybe using quantum algorithms that are not exactly heuristic, but at least are probabilistic, we can produce better solutions, systematically produce better solutions. This is, I call, better quantum advantage. And finally, they can solve the same problems and produce the same solutions of the classical computer, but using less energy. That is important for any HPC center at the moment. If you compare, for example, the quantum supremacy problems and the energy that consume a classical computer to solve the same problem that a quantum computer can solve, we are taking that the classical computer needs between 1,000 and 10,000 more power to solve the same problem. In my opinion, and our opinion, always the algorithms will be hybrid in the future, with some parts accelerated with the quantum computers. Quantum computers, in our vision, will be quantum accelerators of an HPC infrastructure. And the speed up of the quantum algorithm should be analyzed, taking into account the classical part, the pre-processing and the post-processing, and understand if really we can have a quantum advantage and what is the bottleneck of the algorithm. And of course, the benchmarking has to take into account all the full quantum stack in order to understand the capabilities of the quantum computer. And that's all. Thank you to these people that has helped me in the developing of this software and this stack. And I open to questions.
Thank you, Andrés. Thank you for your view on the hybrid quantum HPC computing. And let's see if there is any question for you. I'm not seeing any question, but it's a little bit late. I can understand. We are talking about, okay, there is a question. So have you already evaluated your benchmark suite to real QPUs?
Not yet. We are developing inside the project the first cases, and after evaluating then using emulators, we will move to evaluate the suite in quantum computers, maybe in 1 year or 1 year and a half.
Very good. Okay. Thank you, Andrés. If there is no any other question, I think that is time to move on.